Right, I guess I'm sharing my screen. I guess so. It's yeah. Um, so welcome all to the sixth session uh, of live interaction for the course of Engineering Thermodynamics, uh, NPTL NOC 2026 AE15. Um, the course is a rerun of the original course offered by Professor B.P. Mishra of IIT Kanpur. I am Shrey Sahai Gupta. I am the teaching assistant. I'm a PhD student from IISc Bangalore. Um, I'm in my fifth year, and I've been taking other NPTEL courses as live interaction TA sessions. I've taken other courses as well in previous semesters, and I have been with you for the past five lectures. We are seven more lectures to go. To be honest, this is like half of the course done because we are now at the sixth lecture. So by today we will be half done by the half done of the course. So let's start. A few people, but I don't think so. Anybody is here. So in that case, let me continue and discuss whatever questions I have. Um, and at the same time, happy Holi to everyone. I guess that's why attendances might be also low. Uh, anyways, so let's get started. So we have a couple of questions, objective type. Let me write those down for you. So the first question of the day is another thing. So one important thing about this part is, so we are looking at energy analysis or the first law analysis for steady flow process. Steady flow processes, yeah. So now what are steady flow processes? To just uh, get over with it, let's quickly review uh, what steady flow processes are. So generally, for a general system, uh, open system, for an open system, this is how you write conservation of energy. You say that the rate of change of total energy of the system can be, so the total energy of the system can be changed by three components. One is by mass. So there is a mass component to it. So if you have uh, multiple inlets into your system, then they will have an associated enthalpy coming in into your system, and that will add mass to your system. If you have multiple outlets, then this should decrease the energy of your system, total energy of your system. And note that because we are interested in the rate of change of total energy, we will look at to look or we'll consider flow rates rather than total mass entered into the system or so on. And then the other components are the heat transfer rate, which is Q dot. And then again, another term is rate of work done or the power added to the system or power of the surrounding on the system. Basically, work component added to the system, but in the per unit time form. I don't think I've missed anything else. Let me quickly check also if I have missed any term. I don't think so though. Um, but just to be on the safer side, let me open up on a different uh, screen, open up my textbook, thermodynamics textbook. And just check if I've written the right thing. The thing seems to be less fine. I think. Just give me a second. Okay, one important thing which I missed. This should be, so this should be actually H plus kinetic energy plus potential energy. Okay, so this is important. See, I missed an important part. So it is important. It should be total energy component, not just enthalpy. Enthalpy is kind of a thermal component of your inlet stream, but there can be other mechanical components also, which is kinetic energy and potential energy for a simple compressible system. So for a system which do not have surface tension effects and magnetic effects or electrical energy effects, then this is the most general form of energy conservation. Now, steady flow processes are ones which have their uh, left hand side 0. So this steady flow process LHS equals to 0. Okay. So there is no accumulation of total energy in your control volume or in your system, whatever you're interested in, your like your region of study. There is no accumulation of total energy in it, and then this becomes a steady flow system. Okay. Now consider a steady flow heat exchanger involving two different fluid streams. If the amount of heat lost by one fluid be equal to the amount of heat gained by the other, pick the correct statement. So what are the statements? So the first statement we have is this. Okay. And then there are these options. Okay. Essentially saying that one option is this, then the other option is this. Fourth option is this, where both of them are not equal. So how do we solve this problem? Let me first uh, okay, now, so quite okay. So now note that there is no so essentially when we write this thing, and this is a heat exchanger. Mind that this is a heat exchanger. It is told to us this is a heat exchanger, and it's a steady flow heat exchanger. So the as I said, LHS equals to RHS equals to 0. Now amount of heat lost by one fluid be equal to the amount of heat gained by another fluid. So note that there are two streams, so there will be two inlets and two outlets. Assuming that there is no mixing happening inside this heat exchanger, which is again very probable. So we can't say it might be a mixing chamber, but anyways, if a heat exchanger is said, generally we'll assume that the two streams are not mixed. In that case, the total energy leaving, there is no heat interaction with the surrounding as such, unless uh, so if you would note here, it is kind of saying that this component has to be 0. Okay, this is what it will mean. So in a heat exchanger, generally we are able to write this kind of thing: m dot cold stream h in minus h out equals to m dot h and then h in and then h out. and this will hold for the hot stream, and this will hold for for the cold stream. Another thing to note here is when I said that steady flow processes are defined by this process, so let me write in uh, mass and energy conservation. So steady flow processes essentially means that there will be no changes with time. So there will no be though there will be no accumulation terms remaining. That's why dE by dt is zero. So in that case, for a heat exchanger, this is generally what we see. So essentially, this is saying that these summation terms cancel out, and in that case, Q dot plus W dot has to be zero. Now in a heat exchanger, you are sure that there is no work done on the system. Essentially, there is no work being done on the system. So W dot is zero, and so accordingly, delta Q. It should be Q actually. There should not be any delta or anything, but it should be actually just W and Q. Okay, delta W or delta Q does not make sense because, as you know, these are not state functions; these are path functions. So the delta is generally used for change in a state function. So we should be writing this thing, and this should be W dot and Q dot, but I don't mind. We are abusing notations, but that's okay. But in that case, with W dot and Q dot both are zero. So that's the first answer to the first question. Let's look at the second question. Which of the following option characterizes a throttling process? Okay. Now throttling is an interesting thing. I might Let's spend some time on throttling. It's an interesting thing. Okay. So which of the following option characterizes a throttling process? These are the four options I have for you. Okay. Indeed, it's a quite an interesting. Maybe we can have some discussion on this part. Because throttling is not generally that well discussed, or it's not discussed to a good depth in generally in introductory courses like this one. But anyways, so throttling processes are kind of defined. Note that I'm using the word defined here as H dH is zero. So the flowing stream will observe this kind of behavior, that its inlet enthalpy will be equal to outlet enthalpy. And the idea behind it is that as you saw, I wrote this equation, right? In a throttling process, there is no work being done, so that this component goes off. It's a so throttling processes are characterized or are they're defined by the fact that there is no work done that happens, and also we say that there is no heat transfer also. There is no heat transfer also. So you might be tempted to say that this is an adiabatic process. It is not, okay? In a loose sense, you can say it is an adiabatic process, but again, note that when we say adiabatic processes or isochoric, isobaric processes, generally these are for constant mass processes or constant when you have control mass rather than control volumes, okay? In that sense, you can say this is an adiabatic process if you mean that your system is not exchanging any heat with its surrounding. That's okay. But the idea, so essentially, adiabatic condition is too general, and in that case, essentially you get this. And if you have a single stream, so this m dot dependence also goes off. If you have a single stream, okay, then what you will have is the summation will also go away. And then in general, what you see is that your kinetic energy and potential inlet and outlets are generally at the same height, or if there is a difference, it might not be very important compared to the total enthalpy or the H component in these two terms. And then kinetic energy is also something very low. Okay. Maybe we can discuss when is the kinetic energy, what conditions can we actually neglect, under which that can we neglect kinetic energy. Okay, that is something important. So here you see that this will reduce to H in equals to H out. And now the question arises, uh, velocity decreases and pressure increases and so on. Okay, so what happens during throttling processes? Uh, so let me open up this textbook to see how this throttling process is defined. Okay, I think throttling is somewhere discussed. Throttling valves. So generally, that is how they are used. They are called as flow restricting device. So one thing is that they are characterized by flow restriction, which means what? What does it mean? Does it mean the velocity will decrease? Uh, See, what is flow restriction? Let's try to understand what is flow restriction. Okay. Let's try to understand what flow restriction is, and that would require us to actually discuss the Darcy or the friction factor. Essentially, this equation, which you might be aware of, delta P equals to F L by D, and then you write half rho V square. So if I may say, a long pipe is also a throttling process. Okay, mind that. And but you might say that so let me write this. Okay, what are throttling processes? Claim. So I'm claiming something, and let's discuss that claim. A long pipe is also a throttling device. Why do I say so? See, and so the textbook says so. Let me write this. Textbook uses or mentions flow restriction in the first instance. So the first thing this book talks about, it does not say enthalpy is constant, or it does not say no work is done, no heat exchange is happening. It mentions flow restriction. Now, what does flow restriction mean? Are you trying to say that the flow rate at the inlet will be lower than, so the flow rate at the outlet will be lower than the flow rate at the inlet? Does that, would that count as flow restriction? What do you think? Would flow restriction should not mean? Or let me write this down. Is that what flow restriction should mean? So don't get this word is actually very ill-posed. It does not convey correctly what it means. Uh, Wrong, very wrong. Okay, just mind that it's indeed very wrong. Or two. Okay. Anyways, let me do this, and this is not the correct idea. Flow. So the next word it mentions is pressure drop. Okay. Please mind, it uses the word pressure drop next. And that is what I have written down. So a very long pipe. So this is the important thing. Throttling processes are defined by pressure drops. But particularly saying that pressure drop, you'll see that a nozzle also causes pressure drop. Okay. So pressure drop is not the what do you say, correct way of looking at throttling processes. Okay. pressure drop is not the first. It should not be the first instance word. Pressure drop is not associated directly with throttling processes, although that is the large effect that is happening there. But throttling processes do imply that there is some kind of flow restriction. So first, let's understand what a flow restriction is. It is definitely not that the flow rate at the inlet will be higher than the flow rate at the outlet. Why? Because that violates mass conservation. That will violate mass conservation under steady conditions. Under steady conditions, we know that the inlet mass flow rate should be equal to the outlet mass flow rate, isn't it? So in that case, we cannot have outlet flow rate different than how outlet flow rate different from inlet flow rate. So then what do you mean by flow restriction devices or flow restriction? Essentially, this is used in the context of valves. Okay, in context of valves. Consider a pipe. Consider a pipe. Okay, consider a pipe. How can you how in a pipe? How can you you have a pipe? Okay, you have a pipe and you have some reservoir. Okay, let's discuss why this flow, from where does this flow restriction word come from. Okay, let's discuss that thing so that you guys understand what is going on. So suppose you have two tanks. Okay, you have one tank and that's filled up to the brim, let's say, and then you have a smaller tank, and you know that if there is a difference in the heights, isn't it? If there's a difference in the heights, then you know that there is a difference in the pressures at the inlet and the outlet, isn't it? Uh, to front, and maybe I just write something of this sort. We expect this thing to be there, right? I'll bring this to front, and also this one also bring to front. Now you see, now in a pipe, so now this equation that I have written down, this is called a Darcy-Weber friction factor, or no, it's called what is this equation called? It's called the pressure drop equation. Okay, it's essentially the momentum balance. Basically, you're saying that the pressure force will get balanced by the viscous forces in a steady in a pipe or in a steady flow process. Your friction forces must get balanced by your viscous forces in a fully developed flow and all those kind of things. We'll not get into what is fully developed and all those things, but essentially what we're saying is that in momentum equations, there are a few terms. There is a pressure force, okay? Then there is a viscous force. Now, in a pipe, what happens is, in a long pipe, viscous forces and pressure forces are the most dominant forces, most important forces. Okay, and indeed, the inertia forces, or what do you say, flow rate does not vary in time, or it flow rate at any position is the same at any position and in any time it's the same. So because of that, there is no acceleration, local acceleration happening, or so there are no inertial forces. Let's settle on that. Let's just assume that, or let's just go by my statement that there are no pressure inertia forces in a pipe, and there are only two forces: pressure force and the viscous force. Now, what it says is that because of viscous forces, there should be a pressure drop, and that pressure drop, and because there is a viscous force also, there should be, because of flow, there will be viscous forces, and because of viscous forces, there will be a pressure drop. Now, if so now you see that I can actually convert this, and I can write this thing as rho AV, right? Rho AV. So if I know the pipe uh, cross section area, then I can actually write velocity in terms of flow rate and cross section area, right? So V becomes m dot by rho AC. So A, let's say. And now I can actually substitute this thing back there on, maybe let me write this part only. A is pi. This is d to the power square, and then we have a term called as, and this should be 4. So now if I put this thing into the first equation, this is what I'm going to get. Okay, let me do that part. What I'm trying to do here is, generally you will read the term flow restriction, and then they will also throw a term as in pressure drop, then temperature rise and temperature enthalpy is constant and all those things. I'm just trying to first motivate why flow restriction is coming. Okay, that is an important part. So now if I put in this, substitute the value for V, what I have is 8L, and then this becomes m dot square. This is m dot square, and then you will have rho square, so there will be a rho here, and there will be pi square here, and d to the power q, no, d to the power uh, 5, I think, d to the power 5, yes. So what else is there? FL by d. I think this is fine. Maybe sometimes I'm not think this is okay. Okay. Now you see that there is a direct relation between the flow rate and the pressure drop. Given this equation, if you have a pressure drop, the pressure drop directly, so between two reservoirs or between two, across any pipe or any mass transfer device, which is generally pipes. Okay, in any piping, you're transferring mass from one position to another position. That is called pipes, right? Uh, Across a pipe, the pressure drop is directly, or actually, it depends on the square of the flow rate, right? How would you now? Here you can see, for a given pressure drop, you have a given flow rate, right? Right? What is a way to so for a given length of pipe, what is the way to reduce this flow rate? Or let me correctly put it like, so right at this point of time also, it will not be very clear. Let me uh, let me see. Wait. Right, okay. So you see, for a given pressure drop, pressure drop or pressure weight difference. Let me say not pressure drop. Let me say a pressure difference. So for any given pressure difference, what you will observe is that your mass flow rate gets uniquely defined if all other parameters are kept constant. But there is one term which we can actually use to our advantage. If we want to control the flow rate between these two reservoirs, we actually use a valve, right? We open the valve, we close the valve. What essentially is happening there? Essentially, for a valve, you can write something like this. Rather than writing for a pipe, we actually, for a valve, this is what the equation can be written. So pressure drop across a pipe was given by this, but for a pressure drop across a valve can be given by this K. And this K is directly proportional to the how much the valve is open. So if now you note, for a given pressure drop or for a given pressure difference, you can regulate mass flow rate by regulating this K. So essentially, if I had a valve somewhere here, this K would have come up in along with m dot square. If I increase for a given pressure difference, if I increase this K, my flow rate should go down. And if I decrease this K, my flow rate should increase. This is the reason why valves are called flow restricting devices. This is the reason. They're not called flow restricting devices because they decrease the flow across them. They're called flow restricting devices because you can regulate the flow by actuating these devices. You can increase or decrease the flow rate. Okay, you can also call them flow regulation devices. Okay, actually you are not just restricting device, they are not just restricting it, you are also regulating it. But to be honest, suppose if you had a fully open valve, fully open, then it is a simple pipe. A valve only comes into the picture if you kind of close it. That's the reason why it's called flow restriction. So if you have valves, you kind of restricting the flow by actuating it. That is why these flow restriction comes. Now note across a pipe, because F is like a function of Reynolds number, and then Reynolds number is a big function of m dot. So you will see if I actually substitute for F in terms of m dot, you can actually see that F dot is not independent of mass flow rate. So for a pipe, the pressure drop and the mass flow rate is uniquely dependent, or the friction factor does not, you cannot regulate the friction factor. Only for the valves you can regulate this K. For a pipe you cannot regulate, right? There is no, you can't control the surface roughness of the pipe. Once the pipe has been manufactured, that pipe is there. You can't play with it, or you can't regulate the flow in the pipe. So now what I'm trying to say here is, whenever you, okay, so now when you have an valve in somewhere here in the pipe, you will have an additional pressure drop across that pipe. You will have an additional pressure drop. Do you understand? This pipe has its own pressure drop. But if you introduce a valve in between, an additional pressure drop will has to come up. That's why we say across a valve, pressure has to drop. That is what this is happening, right? Because if there is a flow across this throttling device, pressure will drop across this device. So this is why it is said. So these are two different things. Flow gets restricted by actuating the valve, but pressure drops across these valves by virtue of their existence, or by virtue of flow. Because there is a flow across these devices, the pressures are known to drop across them. Okay, so that is the idea. So in between these 2 points, definitely these two are not correct, because pressure has to drop across flow restricting devices. But as I told you, this is the momentum balance of the equation. So we have three conservations, right? In thermodynamics, you generally don't look into the momentum conservation. That is what fluid dynamics is for. Fluid dynamics is for. But for this one, for once you solve the energy conservation of these throttling processes, you see that the enthalpy at the inlet and the outlet should, what do you say, be equal, but the pressure should drop. Now, what happens for an ideal gas? So if your H of T, this thing I told you, right? For an ideal gas, H is a function of only T. Now, for an ideal gas, PV is actually RT. Okay, so for an ideal gas, because enthalpies are not changing, temperature should not change. But for a liquid, what happens? For a liquid, we know that P drops, and for a liquid, we also know that it's roughly a constant density. Constant the inlet density and the outlet density will not change, right? They will be almost equal. In that case, this term, see, H has to remain same, but PV term is decreasing, which means what? That U, or the thermal internal energy, has to increase to keep the uh, same enthalpy, right? Now, what that would imply, that pressure decreases. Okay, this is not asking me for whether velocity temperature decreases or not, but generally for a liquid, your temperature will increase, okay, during throttling. That is the important part. Okay, so for a throttling process, for a liquid, throttling generally drops the pressure, but in general it depends on the Joule-Thomson coefficient, which I'll discuss later on. Okay, I'm not discussing right now. But here, what about velocity increase or decrease? Okay, so now because pressure will decrease, okay, okay, that this is important. So because pressure, now what is m dot? We know that flow rate has to be also same. M dot in is equals to M dot out, isn't it? That is what I was saying since then, from the very starting. So then this is a constant. Flow rate and enthalpy are both are constant. So this is rho area, let's say inlet area and the outlet areas are also same. And then V. So let me remove this A and say this is proportional. Now, rho is what? P by RT. Okay. Now I know that P will drop. Okay. What about temperature? Or what about density? Uh, about density. So if we get to know what happens with the density, then we can say that velocity increases or decreases, right? Generally, we can't say velocity will increase or decrease. Uh, but what is the suggested answer here? Velocity increases and okay, let me think. What happens for a liquid density? Okay, for a liquid, density is not going to change, so velocity is not going to change generally for a liquid. For ideal gas, again, temperature is not going to change, but pressure is going to drop. Okay, so pressure is going to decrease, but temperature is known to us that it will not get affected. So pressure will decrease, so velocity will increase. So this is the option, but that this is only true for an ideal gas. This is important. Only for an ideal gas that this velocity gets increases. Okay, only for an ideal gas. So let me write this. This is important. I'll write ideal gas. Okay, ideal gas. IG. Okay. This is the important part. So there are a lot of throttling ways of doing throttling things. It's an adjustable valve. You can have a porous plug. Now, so the way to look at it is as I said, no, introducing any throttling device in your piping system adds additional pressure drop. Okay, it so for any so you see here uh, effectively if you add any so see if you have if you introduce an adjustable valve in your piping or a porous plug or a capillary tube in between your pipe, essentially what you're doing is you're increasing your frictional factors or frictional component. Okay, you're increasing the viscous effects, which for a given pressure drop will decrease your flow rate. Okay, that is why they are called throttling or flow restricting devices. Just note that part. I think this has been covered loosely in your video lectures, but anyways, I just discussed some uh, important, like just some like I thought this is the missing part from what is generally discussed. Okay, so which of now the next question is this. Let's look at the next question. One of the following indicates unsteady flow processes. So in an unsteady flow process, as you know, there will be what do you say? There will be there should be accumulation of energy or depletion of energy or depletion of mass or depletion of accumulation of mass. Okay, so these things should happen. Now, flow through a turbine can be a steady process. You might know that. So this is not the answer. Although the flow through a turbine can also be an unsteady process. So for sure, we can't say for sure. For a turbine, we can't say generally. But anyways, in general, turbine can have steady flow process. Mixing of three fluid streams can also be an unsteady process. Inflating tires of a bicycle can never be steady. Why? Because you can't continuously keep on steadily adding air into the tire. There is a mass accumulation that is happening. Okay, flow through delivery pipe of a reciprocating pump. Again, reciprocating pump can be time averaged to get unsteady flow process. It has to be, again, note that reciprocating pump uh, is in general it's not steady. Okay, it's in a reciprocating pump there are four phases, uh, or there are two phases. There is a compression phase and then there is a suction phase, then again compression phase and so on. So in a reciprocating pump, it is not ideally a steady flow process, but when you time average it over one cycle, then you can actually think of it as a steady flow process. But inflating tires of a bicycle for sure cannot be a steady flow process. Okay, because there is a mass accumulation. If there was an energy accumulation, then also this would happen. In a reciprocating pump, at least over a cycle, there is no net energy transfer, net energy accumulation, or net energy mass accumulation, right? So that's why this is also not a, like, these are loose answers. Okay, to be precise, turbine can also have unsteady flow process. Mixing of three fluid streams can also be unsteady. But out of these four options, if we had to select, we'll select the third option. That is the most appropriate of all these. Okay. The next question is this. Almost what I discussed. Which of the following option is correct? Throttling is an isentropic process. Uh, Throttling is an isenthalpic process. This is something which I already told you. Throttling is an isobaric process. This you know that it is not true. Pressure has to drop. Throttling is an isochoric process. By no means we can be sure of it unless the flow is it cannot be isochoric because it's not a it's because pressure is dropping. In general, you can't say that it is an isochoric process or not. For an incompressible flow, maybe, but otherwise you can't. Okay, this is also not an option. Throttling process is known to be an irreversible process. Okay, this is the first process that you're learning of, which is an irreversible process. Okay, throttling is an irreversible process. We can actually see this. So for the if you have the same enthalpy across a stream and your pressure is still dropping, we can actually see for an ideal gas at least uh, that this has to be a non-isentropic process. And I'll tell you, entropy must actually drop. Okay, so let's look at this. If you in a future lecture or somewhere, you will come across TDS relationships from which you will learn how to actually calculate entropy change. So in that one, you generally write this, right? Delta S is Cp. Okay, delta S is Cp ln T2 by T1. Okay, minus R ln 2 by P1. This is something that can be easily derived. Okay, I'm not deriving it here, but this will get derived later on in the code, or maybe it has already been derived. Now you see, for an ideal gas, I showed it to you that the temperatures in the inlet and the outlet remain same. So T2 and T1 are inlet and outlet temperatures. So this thing gets cancelled. So you only have this. Now, because you know that P2 is less than P1, because I told you, no, pressure drops. You see that this minus sign which gets cancelled because ln something less than 1 has a negative log value. So this minus and this minus gets cancelled. And so you will have a positive delta S. So this is known. And actually entropy is also known to only be reversibly affected by heat transfer. So if you know that this is a adiabatic process and your entropy has increased, so for sure you know that this delta S is actually S generation. So actually we can also write this thing. Actually delta S gets delta S, or the entropy of the system, can get affected by two things. It can be a mass effect, the system mass has changed. For a constant mass process or for a steady flow process, you can have delta S due to heat transfer, and will be an irreversibility. So for a throttling process, we can actually show that this is a irreversible process where entropy kind of increases. Okay, so this is important. And let me here just quickly write for people that P2 is less than P1. Okay, so again, this is also okay. Maybe we'll move to the next question now. Okay, this question is a simple one. This is a true and false question. The question is, the size and shape of a control volume may vary during an unsteady flow process. Definitely, like I have a very quick example on the same page. Inflating a tire, as I told you, you see that the size and the shape, both of it, changes during an unsteady flow process. And so this statement is true. Okay. So nothing to be, nothing sacrosanct here. We can move ahead to the sixth question now. When is the flow through a control volume uniform? When the flow through a control volume is uniform. What do you mean by uniform flow? Uniform flow means, note this down, uniformity means that there is no variation in space. Steadiness means no variation in time. Uniform means no variation in space. So when the flow through a control volume uniform flow, okay, so it's asking mass flow rate as a function of space. When will this be uniform? Uh, it should be uniform for an steady flow process, okay? So involves no changes with location at any specified time. That is true. So this could be an answer. Involves no change with time at any specified location. This is exactly the definition of steady flow process. Involves no change with location all the time. So uniform flow may be unsteady. It's not that it should be also not a function of time also. So involves no change with location at all times. Uh, Seems like it's trying to say that at all times it should be the same. So that's not true. Okay, involves no changes with time at all location. This is again definition of very. This is a steady, unsteady, uniform flow. That's not true. Okay, so the true answer is no changes with location at any specified time. Okay, so now I guess we have a question on numerical question. 2, 3 numerical questions we'll do, and then we'll close today's lecture. Okay. So steam enters a nozzle at 400 degrees Celsius, 800 kilopascals with a velocity of this much, and leaves at a temperature. So inlet pressure are given. Outlet temperature and outlet pressures are given. What are we asked? We are also told the heat rate at which it is losing, and the inlet area is given to us. Determine the velocity and volume flow rate of the steam at the nozzle exit. Okay, simple, just mass conservation, energy conservation, nothing else we will do here. Um, so one thing which has been told to us is that we know rho in, right? We know rho in because our inlet pressure and inlet temperatures are given to us. Okay, so first let's find out what is rho in. So that we will find out using property tables. So let me pull up the property tables here. I'll have to pull them up. See. Right. So we have 400 degrees Celsius and 800 kilopascals. Let's go to the steam, superheated steam. Okay. Steam table I'll have to go to superheated water. So first of all, 800 kilopascals and then 400 degrees Celsius. And so 800 kilopascals is this, I think, 0.8 megapascals, and then 400 degrees Celsius is this one. So this table is the important table, and this gives you the specific volume. So we have V in. This is the V in, okay? I'll write it as this. Rho in becomes this thing. Now we know rho in, and I need to calculate volume flow rate. So now we know inlet area and we know velocity first of all. So volume flow rate should be quickly, we can write V dot or volume dot is what? A into V, right? A into V, which is like zero point 0.8 meter cube. No, no, not 0.8 meter cube, 800 divided by 10,000. So this thing gets cancelled. So 0.08, okay, 0.08 into 10, so which is like 0.10. So 0.8, sorry, 0.8 meter cube per second. This should be our uh, this should be our answer. Okay, this should not. Okay, but it is asking at the nozzle exit. So this is at the nozzle inlet. Okay, that is important. I didn't. Yeah, I didn't see that. Then I also need to calculate the velocity at the inlet. So again, I'm also given the row outlet, right? Because the same properties are known to me. So let me calculate at 200 kilopascals, 300 degrees Celsius. Okay, so let me pull up the same table. 200 kilopascals is zero point 0.2 megapascal, and then 300 degrees Celsius is this. This is the specific volume. So 1 by term, and then we just write rho in, A in, V in equals to rho out into dot. Let's calculate the volumetric flow rate. Okay, rho out. So this should be what it should be. V out should be dot V. This should be V in and then V out divided by V in. So this thing has to be 0.8 times 0.38429 divided by 1.31623, and let me use the calculator to solve this. Point 0.8 into 0.38429 divided by 1.31623. It's 0.23 something. Okay, wait. This should be V out by V in. What have I done? It should be V out by V in, not V in by V out. Uh, case, the answer comes out to be 2.74. Okay, 2.74 meter cube. What else is asked? Velocity. So, okay. So for this, I think we'll have to use, what do you say? Our equation for this thing, a steady flow equation. This is a steady flow process. Okay, this is a nozzle, right? This is a steady flow process. So in that case, we can say that m dot dot. So there's only a single stream. So this becomes m dot h in minus h out plus dot q. And there's no work done as such, right? There is no work done on the nozzle. This thing is zero. So W dot is known to us as to be zero because we are not doing any work on the nozzle. Then Q dot is told to us to be, what do you say, minus 25 kilowatts. And then mass flow rate is known to us. That is like 1 by 0.38429. And then this is 0.8. So this is the mass flow rate, by the way. H in and then H out, let's calculate. Okay, there's another thing. We should have uh, plus. So there's a kinetic energy component that I forgot, isn't it? This should be m dot, and that kinetic energy in this is what m dot v square by 2, and this should be v in and then v out. This is why this is how we would use this conservation of energy to find this thing. Okay. So now H in and H out can be calculated directly from the tables. So let's do that. We'll move this here. So let me first calculate what m dot is. Okay, let me calculate what m dot is. So, so m dot is around 2.08 kgs. Okay. Point 0.08 kgs per second. Then let's calculate what H in and H out are. We'll use property tables for that. So this one, let's see what H out is. H out is this 3072.1. Okay. And what is our H in? H in is this one. So you see that it is kind of losing enthalpy from inlet to outlet, isn't it? Then Q dot is again, there is an energy loss also. So in that case, what is H out minus H in? Let's directly look at it from this data. So 267.7 minus 72.1 is minus 195.6. So now if I solve this becomes 2.08, and then there will be a minus sign times 195.6, and then you have 2.08, and then you have v square. V square is 100, so it's 50 minus v square out by 2, and then this is minus 20,250,0 3 zeros, and this is 0. isn't it? So now you take this 2.08 and divide this thing. Okay, wait. Divide by. Are in kilojoules. I think this will not be 25,000. This will be only 25. See, these are in kilojoules. So this has to be only 25, not 2500. I should mind that. 2.08. Okay. Now this 25 by 2.08 will roughly become 12 point something, right? Less than 12 point something. So exactly 12.02. So this is, let me copy this. Essentially we have, so this plus 50 gets cancelled. This V square can go on the right hand side. And you have 50 here, so this will become minus 145. And this is minus 12.02. Okay. 12.02. Now, if I add this to 145.6, so this becomes 150, which is just give me a second. So this is H in minus H out. Okay, note that I just didn't. This is H in minus H out. So you have 1 minus this thing is there. So this gets added up to become 245. Now 245 minus 12 is 233.58. So this is 233.58. And now V square is 467. V comes out around 21. According to my current calculations, V is around 21.61 meter per second. This is what I should get, but let me check if I've done this correctly or not. Not done it correctly. Okay. What have I done incorrectly now here? Ten and 100. That's okay. 25 kilo. Let me check. Check. Okay. And had I made a mistake somewhere or not? So I have a reference solution to this question. So fine. Okay. This should not be 50 by 100. Okay. By the way, this should be 50 by 100 because we are considering everything in kilojoules. 50 by 1000, first of all, because we have everything is in kilojoules, right? This I've taken 25. V square has to be also taken in kilojoules. That is one thing. Mm. Oh, I get it. See, this is first of all, this should be. Let me cancel this thing. So this will be 0.05, right? 0.05. So this will become 195.65, first of all. Then this will be minus 12. So then this becomes 19. So in the final step, I've made a mistake. 195.65 minus 12.02 is 183. While calculating V square, I actually need to calculate it in terms of kilojoules. So this will be, there will be a zero here, 630. Okay, into 1000 into 2, and then I take a under root of this. So then we will get V as 606 meter per second, which is the correct answer. So in the final step, I made a mistake because I am doing this a little quickly. You don't do that. Do that slowly so that you don't make mistakes of such sort. Okay, now let's spend some more time into another numerical problem. Okay, I'll take a quick break and then come back. Let's look at this question. An adiabatic air compressor. So first of all, adiabatic, right? So no heat transfer rate. That is one thing. A volumetric flow rate is given 10 liter per second of air at this much pressure and temperature. And then final pressure and temperature is given. Work that is required by the compressor and the power required to drive the air compressor. First of all, it is asking specific work, which is kilojoules in kg, kilojoules per kg. And then there is power required to drive the air compressor, which is the total work. Okay, so flow rate into whatever. Consider air as an ideal gas. Use Cp to be this, gas constant to be this. Steady flow processes tells you, because it's a steady flow process, right? It tells you that you have to do some work. If you're not doing any and still getting a flow, so then H in minus H out, then there is no heat added, or this is the equation that you will follow. So now, first of all, let's calculate rho in. Which is P in by RT. So this is 120 into R is 0.287 or 287 pascals, and then T is degrees Celsius, which is like 293.15. So this is your rho in. Okay. What will be your m dot? This will be rho in into V. Rate of change, volumetric flow rate, right? Which is what 10 liters per second. So this entire thing uh, into times 10. But then you note that 1 liter has 1 meter cube has 1000 liters. So you convert this into meter cube per second. You see that there's a cancellation that can easily happen, isn't it? This can, after cancellation, you will essentially have just the 10. Okay. Now this is the flow rate, first of all. Now let's calculate delta H. Delta H is what? H out minus H in is what? Cp delta T, right? For an ideal gas. Cp out minus T in, which is what? 300 minus 20, which is 1.018 times 280. 280, isn't it? And this is kilojoules. So this you into 10 to the power 3. So this 1018 into 280. So now your work done. Okay, so first of all, work done per unit flow rate. Okay, so which is delta H. So what this is what it will be. 1018 into 280 will be kilojoules per kg, isn't it? Right? This will be kilojoules per kg, right? Kilojoules per kg. What is this value? Actually, this will be joules per kg, by the way. So if I have to calculate in kilojoules terms, then this will be kilojoules per kg. Then this is 280, so roughly 280 only, right? Roughly 280. But let me calculate it for you. 1018 into 280 is 285. Okay. This comes out to be 285. 285 kilojoules. Then you just multiply the flow rate. So to get the work done, so because this is work done to the system, compressor system, so I'll calculate minus W dot. This will be dot delta, which is how much? 285 times 10 to the power 3 times this entire thing. Cancellation that can happen if we want to go to the rough calculations. Okay, 287 roughly gets cancelled by 285. Then 293 can be roughly written as 300 or 290. 290. Or let me just do this part of it to see what it is. 10 to the power 3 can be taken as kilowatts. So 1200 divided by 293, which is roughly 300. So roughly close to 400. Something we're going to get 4 kilojoules or something, right? 293.15 is 4 kilojoules. Just this is what it will be, 4 kilowatts. So this will be your answer. Okay. If you have to quickly do the questions in paper, don't use too much calculator. If there are rough calculations, then you can just go ahead and solve this, because we had options here. I'll show you that there were options here. So in this option part, you now know that this should be the correct answer. Okay. So you don't need to solve it. You just see that it is close to 4, and this should be the answer. That's the correct answer, by the way. We'll do 2 more questions, then we'll close. This is the next question. Question is, the fan on a personal computer draws this much of air, volumetric flow rate is given, inlet pressure is given, inlet temperature is given through a box containing the CPU and other components. If the electrical power dissipated by the PC components is 1.1 kilowatts. So you know electrical power is some work, okay, and that is going into the box. Determine the exit temperature of leaving air. So you can consider this as a heat component or work component. I don't mind. Uh, but note that even if you consider it as a work component, the outlet pressure is the same as the inlet pressure. Okay, and because of that, this is essentially a work component only. Oh, sorry, this will be a heat component only. So this is basically a heat addition, whatever heat addition is happening. So that is what we need to just solve for it. Nothing much here. So now, if I write this, so first of all, I need to calculate the density. So which will be 1. So 10 to the power 5 by RT. Okay, 287 times 293. So this is my density. Okay, I'm not writing it completely. This is a simple problem. This is rho, whatever I've written up till now. Now I write into volumetric flow rate, which is 0.08. Now the change in enthalpy will be Cp 1.05, 1.0 or 1005. I'll write in terms of joules, right? In terms of joules per whatever. So in terms, not kilos, I am removing. Okay, 1005 into delta T. So there will be a delta T term, right? So T minus 20. This should be equal to 110. Sorry, 1010. 1100. Sorry. So 1100, right? Right. So now let me see if we can make any progress here. This will get cancelled to you for you to get 10 to the power 3, by the way. And then can become 1 to give you 1.100. So 1.1 here. And then we just need to, like, we'll have to use the calculator here. I don't see anything else. 287 to 293.15 divide by 8 divide by 1005 divide into 1.1. So T is coming around 31. Okay, T, this is coming out. So delta T is coming out 11.5. So delta T is coming around 11.5. And so the close answer is 31. Okay, T out should be 31. But now let's do the last question for today and let's get this thing going. Saturated liquid vapor mixture of water called wet steam in a steam line at 200 kilopascal is throttled to 100 kilopascals and this much. What is the quality in the steam line? At the outlet, I assume. This is saturated. So one thing is, it is told to us that X inlet or the is 1. Okay, saturated liquid vapor mixture is 1. And then your inlet pressure is known to you, and then it throttles to some temperature. What is the quality in the steam? Okay, so let's draw the TS diagram. That is the interesting part here. The TS diagram. I don't know. I like TS diagram more. I don't like TV or TP. We can definitely draw that too. But this is how the TS diagram looks like. Uh, Constant pressure lines, and with pressure drops, sorry, I'm drawing it wrong. This is not how it looks like. It looks like this. Now, what are we told? We are told that we are somewhere here, and then it throttles because it goes to lower pressure. And as I have told you, it's an isentropic process. So entropy must increase while decreasing the pressure drop. This is how a throttling process looks like. Okay. So in this throttling process, enthalpy remains constant. That is also an important aspect. So H in equals to H out. And you know the pressure. So this way you can actually quickly calculate. Nothing much to do there. Let's first figure out what is our H in. Okay. So for H in, we need to find H at Hg because X in is 1 at T sat of 2 megapascals. Okay, so let's look at the property tables here. Either we can use these superheated water or we can just go to saturated water tables. Go for 2000 kilopascals. This one. Now here, what you need is Hg. That's it. This is what you need. Hg, which is 2798.3 kilojoules per kg. Okay. This is your H in and also your H out. Now, okay, let's see. So now is you're told that the final pressure is 100 kilopascals. One important thing here, now that we know that the pressure drops, entropy increases, we are for sure in the superheated regime. That is the important thing. We cannot go like down unless it is told to us that there is some uh, heat exchange happening or some, this is a non-adiabatic process. But because there is nothing given here, we can see if you try to assume that there will be some heat transfer and it's non-zero, then you will fall in the problem of a more number of unknowns than knowns. So it is you have to actually go ahead and notice that it is only for um, zero heat transfer that you can find out the final quality of the steam. Okay, only then this question is well posed. So in that case, you go to the superheated regime, okay, of 100 kilopascals or atmospheric pressure, right? So there we will go for superheated regime. Superheated is 100.1 kilopascals, 0.1 kilopascals, well, zero point 0.1 megapascals, and there you have to find H, which corresponds to what? What is the quality in the saturated liquid vapor mixture? Let me think.
Okay. Because in that case, X out will also be 1. Does it mean that it is somewhere here? Saturated liquid vapor mixture. I don't know why someone would call this saturated. Both of them are saturated liquid vapor. Saturated liquid vapor mixture. Okay, fine. I'll take this one. Otherwise, this question won't make sense. Okay. So I have to take not this, but HF here. So let me correct this. So in that case, if I go back, use that saturated steam table to go to 200, then I'll use this HF value 908.47. This should be my table. Sorry, this should be my enthalpy. And then I use the two-phase table again at 100 kilopascals, which is this one. So now you see here your HF and HG are these two values. So from this, you can quickly calculate X. So what is given to you is at pascals is this, and then Hg is also known, or HFG, wait, and let me use HFG here. Now you just need to substitute X to find this value. So what essentially you have is 417.51 plus X times of 2257.5 gives you 908.47. And so you just calculate this for X. That's it. You're done. Okay. So now let me do this part. So you get 908.47 minus 417.51 divided by 2257.5. Your answer should come close to point. Wait a second. Am I getting a wrong answer here? Point 2000 kilopascals. I done something wrong. Let me check. 2000 kilopascals is this. So I took HF 908. See, if you are in a saturated vapor zone, then definitely you cannot get a quality lesser than 1, lower than 1. Definitely you have to be in the liquid region, 908. But at 100 kilopascals, Hg is very high. Okay, let me see if I'm making some mistake somewhere. It's throttle to 100 kilopascals and 120 degrees Celsius. Okay, that is also an important clue. I didn't check that. See, at 100 kilopascals, the saturation pressure has to be 99.61. If it is higher, okay, wait, I think. Wait. This is not the way to do it, but wait.
Okay, so that is what I've this is incorrect. Got it. How to do it? I got it. I was making a mistake. Okay. So actually, it is not told to us that it is saturated or unsaturated. I made a mistake somewhere. Essentially, what it is saying is that somewhere here, we don't know where it is, and it goes to this direction. Our outlet conditions are told to us because this pressure and this pressure is told to us. So we'll back calculate H in using our outlet enthalpy. So this is not the way to do it. Okay, this should be. Let me correct this. This is incorrect. So H out should be H of 100 kilopascals. So this is a superheated state that we know. Okay, that is important. First, let's calculate. Let's see what that is. So we go into the superheated regime. 0.1 and you go to 120. Okay, so you calculate this. What is our H in outlet? So the way to do it is 2675.8 plus 2776.6 minus 2675.8 into 2 by 5, which is 2. So basically, you first find out this enthalpy, which comes out to be 2716.12. Okay. Now you use this equation at 200 kilopascals, 2000 kilopascals. Okay. So first we find this out. So for that, we go to the saturated table. A mistake there. The lingo is that saturated vapor, we don't know what Xn is. We actually need to find it. Okay. That case, that is the case. Let me just quickly calculate it. 2716.12 minus 908.47. Then you divide this by 1889.8 and you get the answer as X equals to 0.96. Okay, so that's how you calculate it.
So I made a mistake in considering that Xn is known to us. It's not. Saturated liquid vapor mixture is known, but it's not told how much quality it has. Okay, so that's how you solve this question. At this point, let's stop. I think this is a good session, and happy Holi to everyone, and please enjoy. So meet you next week. Okay.